Today we'll discuss a very different method to what we've been seeing so far, and it's known as the slice rank method. It was developed in 2016 to understand sets that contain no three-term arithmetic progressions. And I should say that the main idea was underlying in this paper that was considering sets in Z4 to the n. While the big problem, it was in Z3 to the n. The idea was still in here. And just a little later, Ellenberg and Gijswijt generalized it to Z3 to the n. So the exposition I have here is a reformulation of this method by Terry Tao, which appears in his blog. Okay. So what is a cap set in Z3 to the n? It is a set S inside Z3 to the n that has no three-term arithmetic progressions. With no three-term arithmetic progressions. And the question is, how small is this set relative to the ambient space? So how small is S relative to Z3 to the n, which of course has size 3 to the n. Let's just understand a bit better what an arithmetic progression is in this setting, because we're probably more used to them in the integers, in the setting of integers. So 3 points that are vectors now in Z3 to the n form an arithmetic progression if and only if there exists a d that's non-zero, not a zero vector in Z3 to the n, such that b comes from a by adding d, and then c comes from b by adding d again, or a by adding to d. Okay, so this means immediately that as soon as you have your first point A and the heading D, then you go to B, and then you add that to go to C. So the points A, B, C actually are collinear. So that's equivalent to A, B, and C being distinct and collinear. And in fact, they form a full line inside Z3 to the n. Every line in this universe has 3 elements. So a set without any three-term progressions is a set with no lines. So a cap set is a set with no lines. So we see it sits at the other extreme from Kakeya. A Kakeya set contains a line in every direction. A cap set has no lines at all. Okay. And something that we will use actually is a slightly better, more effective formulation of these 3 equivalent statements for an arithmetic progression. We notice, of course, that all these mean that A, B, and C are different, so this is not a diagonal element anyway, it's not of the form A. And when we add them up, they add to 0. A plus B plus C should add to the 0 element in Z3 to the n, because D plus 2D will equal 0. And it's easy to see that the converse also holds. So whenever you have a diagonal element, of course, the 3 vectors will add to 0 in Z3 to the n. But if for distinct elements you have this equality, then it's easy to see that they will form an arithmetic progression. Okay. So this is an equivalent statement that characterizes progressions. And here is what was known. So in 95 was a non-trivial upper bound on the size of cap sets by Mashulam, who showed that every cap set has size at most a constant times the size of the ambient space over n. And this shows that yes, okay, they're quite smaller than the ambient space. Bateman and Katz slightly improved on this, so they showed it's at most a constant times the size of the ambient space over n to the 1 plus epsilon naught for fixed epsilon naught. And the constant I'm using here is independent of n. And finally, Ellenberg and Gijswijt showed something way better. These used highly non-trivial techniques. Using the sliced rank method, which is essentially linear algebra, they showed that this 3 can be reduced here. So they showed it's at most a constant times 2.756 to the n. And the constant is even explicit, it can be 3. Okay. So this is considerably better, and effectively they they finished the problem because there are lower bounds that are of the form 2 point something to the n. Right, so how did they do that? They used this method that now is known as the slice rank method. And the idea is if you want to control the size of a certain set that usually lives in a f to the n, where f is a finite field, it may be a very good idea to use the structure of the set to extract an interesting matrix out of it. So the idea is, suppose we can construct something like this. A matrix, so these inputs here are elements of the set S that we want to understand. So here I enumerate the elements of S. And here in the matrix, let's say I have non-zero everywhere in the diagonal, everywhere, and 0 everywhere else. Okay, so this is a very special type of diagonal matrix. And let's say that the reason such a matrix exists, is that we use the structure of S. So someone asks why 2.756. We'll see where it comes from, and it's not really a special number. You can get a bit lower than that as well. It's just strictly smaller than 3, and that's the interesting part of this. Okay. So let's say that we managed to use the structure of S to get an interesting matrix. So the fact that these non-zero elements exist along the diagonal follows from the structure. So this matrix encapsulates the structure. So this means that the size of S happens to be the rank of this matrix. Okay. So we express the size as the rank of something interesting. And now the next step is use algebraic methods to understand this rank, to control this rank. So the structure of S falls inside the matrix, and then you try to use algebra and what rank means to understand this rank, to get bounds on this rank. So the point is that you need to construct for this a map. M takes all pairs of S, 2 elements of a field F. And the property should be that the 2 inputs are being sent to non-zero things if and only if they are on the diagonal. Okay. So the point is that if a structure of S has to do with pairs of points in S, yes, it is possible perhaps to create such a matrix because the structure has to do with pairs. But what if the structure has to do with triples of points, just like in the capset problem? We know that no triple forms a 3-term progression. So then we would want a 3-dimensional matrix, really. So we would want a matrix or a map from triples of points in S to F, again with the same property that the value is non-zero if and only if we are on the diagonal. Okay. And we can visualize this as a 3-dimensional matrix here. And I've made red here the diagonal of this cube where all the non-zero elements can be found. All these are non-zero and everything black is zero. So we expect that some sort of rank of M should still be equal to the length of the diagonal. For this is a diagonal kind of matrix, just in higher dimensions. So we still expect that the size of S, which is the length of the diagonal, the number of rows, it should still be the rank of this matrix for some other sort of rank. And then again, for this sort of rank, we want to use algebra to understand it. This rank of this interesting matrix we created. And that's really the idea behind the slice rank method, the interesting notion of rank that would generalize the regular rank to all dimensional matrices is what we will call the slice rank. So let's see some definitions. Maybe the interesting pattern inside S has to do with k-tuples of points rather than pairs or triples. So we're aiming for a k-dimensional matrix. So this is called a k-tensor. But you can think of a k-dimensional matrix if you prefer. And by the way, what is a one tensor? A one tensor would be any function from S to the field. So S has size of S elements, and for every one, we put a different value here. So these are size of S elements. So this just belongs to F to the size of S. We can think a one tensor is a vector. Okay. And generally, a k tensor is a k-dimensional matrix of side length the size of S. And the tensor is diagonal if all of its diagonal is non-zero and everywhere else we have zeros. So if, in other words, M of A1, A2 elements of S, K of them, is non-zero if and only if we are in the diagonal. And again, you can visualize it just like this one. A cube with diagonal non-zero and everything else zero. Okay, so now to generalize the notion of rank, we need to see what we mean by a rank 1 matrix to begin with. So in higher dimensions, a rank 1 matrix will be called the slice. So a non-zero tensor is called the slice if we can write it, okay, it has k coordinates, but we should be able to take one out, to slice one out of the rest. So this should be the product of f of xi times g of x1, the rest of the coordinates of the variables. So if we can slice out one of the variables, this is when we call it a slice. And let's see what it means. In the general case, but I'll draw a picture in 3 dimensions. So here is a slice, let's say. And let's say that the variable that we have decoupled is the x variable. So it is the product of that with a regular 2-dimensional matrix. And let's say that here we enumerate our x, here we have our y's, and here we have our z's. Okay. And let's see what happens here in the front layer. In the front layer, the values, so x is a1. So the values are, we form f of a1, that's fixed in the layer, times m of yz, overall yz. So it's simply a multiple of this single matrix, m. Same for the next level. So for the very final level here, you see that x is fixed, so I have f of a s times, again, the same matrix. So we see that for a slice, there is one direction, in particular the direction of this xi variable, such that all the layers in that direction are multiples of a single layer. So there exists a direction such that all, let's say, rows, k minus 1-dimensional rows in that direction are multiples of the same k minus 1 tensor. So this is in the 2-dimensional case, this is just what a rank 1 matrix is. So for k equals 2, we have that a slice is nothing else than a rank 1 matrix. Okay. Right, so now we'll define the slice rank. As you probably expect, a slice should have rank 1, slice rank 1, and then the general slice rank is defined in a common way as the regular rank, just for higher dimensional matrices. So the slice rank of a K tensor is the smallest R, is the smallest number of slices we need to write it as a sum of those slices. So the smallest R, such that M is the sum of our slices. And of course, this implies that for k equals 2, so for two-dimensional matrices, so if M is from S cross S to F, then the slice rank of M is the same as the rank of M. Because for matrices, the rank is the smallest R, such that M is the sum of R rank 1 matrices. So the definitions agree in 2 dimensions. Okay, and it's not always clear to see from the picture what the slice rank is, of course. So let's just do an example with variables. If we have M of x, y, z, where these say belong to a field, so not in a field to the n, but to a field this time. And this is x plus y plus z in F. Then the slice rank is what? Well, I see that I have one slice here, that's x times 1, so decouple the variable x. And I have another slice here, because it doesn't contain the variable x that has been decoupled. So here this has slice rank 2. Okay. Right. So what happens though for higher dimensional matrices? So we saw that for 2 tensors, for regular matrices, the slice rank is just the rank. Now for higher dimensions, we know, it's easy to see, that the slice rank of M, of a K tensor, is again at most the number of rows in this K dimensional cube, so at most the size of S. It shouldn't be a surprise that any maybe natural notion of rank should satisfy this. But here is a visual proof. You have your matrix, your K-dimensional matrix, and you want to write it as a sum of slices, and you want to use fewer, or at most the size of S slices to do that. How can you do that? Well, one slice can be the matrix that has this front layer and 0 layers after that. That is a slice. And so on. You add all the layers like that. So here this has the second layer lighted up and everywhere else 0. This has the final layer lighted up and everything else is 0. Every one of these is a slice because every column is a 0 multiple of the first. So they are all slices. All right. So what does the slice rank lemma say? So this is the one that you use when you want to count the size of a set using slice rank. If you have a diagonal matrix, so diagonal for us meant that all the diagonal entries were non-zero, that's important. So there is no degeneracy here. So if we do have a diagonal K tensor, then the rank is full. The slice rank is full. It's as big as it could be. In other words, it's the same as the number of rows. So the proof, we'll see it later. For now, let's just see how to use that to prove the cap set conjecture. So S will be our cap set, the set that doesn't contain any arithmetic progressions, 3-term progressions. And we will construct an interesting tensor out of it. And then that will be diagonal, and we will know that the size will be the same as the slice rank of that tensor. So that's the plan. Here is the theorem. If we have a cap set, then its size is at most this. And as I said, the important thing here is not exactly even what this number is, but it is strictly smaller than 3. So, all right, so we fix S, a cap set, in Z3 to the n. The goal is to construct an interesting K-tensor out of it. So construct a diagonal, in fact, K-tensor n from S to the K, from K tuples of K into F. Because then we will know automatically by the slice rank lemma that the size of S, which we want to understand, is exactly the slice rank of this tensor. The K is up to us. We don't have any specification. This doesn't include anything about the K. But to construct an interesting tensor out of S, so using the structure of S, we should think about what K tuples we have information. And their information is about triples in S. We know that no triple of points is collinear, lie on the same line, except if they are the same repeated vector. So let's remember, we know that for 3 vectors in Z3 to the n, we have that A plus B plus C is the 0 vector in Z3 to the n, if and only if either we are on the diagonal, or the same thing, or A, B, and C form a 3-term arithmetic progression. Of course, the same should hold for our set. For any triple of points in our set, that's exactly when we have the sum being equal to 0. However, in our set, we don't have 3-term progressions. So this is impossible to be the case. And therefore, in our set, it's exactly on the diagonal where this triple adds up to 0. So we found something interesting happening on the diagonal for triples of points. We wanted non-zero stuff on the diagonal, not 0 stuff. But okay, if you have 0 stuff everywhere, then I don't know, you take 1 minus that and it becomes non-zero everywhere. Okay, so let's see what I mean. We have, so for every off-diagonal triple, for every off-diagonal ABC in S to the 3, they won't add up to 0. We know that. They will not form a 3-term progression, and therefore they will not add up to 0. This is different from 0, the 0 vector with n coordinates. So one of these coordinates at least should be non-zero. This is a vector with n coordinates. So this is the same as saying that AI plus BI plus CI is non-zero for some I. So it should be either 1 or 2, right? Because these coordinates live in Z3. So this should be 1 or 2 for some I coordinate. Okay. And that's the same as saying that either AI plus BI plus CI minus 1 is 0, or AI plus BI plus CI minus 2 is 0 for some I, and therefore it's the same as saying that when you multiply over all coordinates, this product will definitely be the 0 number inside Z3. Okay. So we found now, by taking essentially 1 minus our sum or 2 minus our sum, we found a form, a tensor. So let's think of this as M of A, B, C, that at least off the diagonal, it's 0 everywhere, which is what we wanted. And now we'll try to show that on the diagonal, it is never 0. So on the diagonal, we have M of A. These are the kind of elements we get. So I go to M, And they replace ai everywhere, so it's 3ai minus 1 times 3ai minus 2. That's what I get. And this is 0 in Z3. So I'm getting the product of 2's from 1 to n, that's 2 to the n, and it's not divisible by 3. So it's not 0, which is great. So we constructed an interesting diagonal K-tensor, 3-tensor, out of our set. So we use a structure at no 3 points form an arithmetic progression to get this. Right, therefore this is the interesting diagonal tensor. It's a diagonal tensor on S. And therefore, the size of S that we were interested in is just the slice rank of this very explicit now tensor. This is the slice rank of M. All I need to do is to look at this very precise M and try to write it as a sum of slices in the smallest, fewest possible slices that I can. Then I will show that the slice rank is very small, and therefore S must be very small. Okay. So how do you do that? You need to study what M is and try to write it as a sum of slices. So we expand it out. So expand M out. Right, what do we have here? For every I, this has degree 2. So you multiply out this xi, yi, zi, you just get degree 2, a degree 2 polynomial. So when you will multiply n times, you're getting a degree 2n polynomial. Okay. So this means that M is a sum of monomials. The monomials will depend on all the variables appearing here. So it's important that the variables are not 3, actually. There are many more, because each x, y, and z, they live in Z3 to the n. So they have n variables in them. So I have monomials in the x variables, in the y variables, and in the z variables. Okay, but of course, the total degree here is at most 2n for every one of these monomials, because that's what happens here. So here, the total degree for every one is at most 2n. Okay, so all these exponents add to at most 2n. And also, we noticed that for every single xi, yi, or zi, the exponent has to be very small. So xi, every single xi only appears here and here in 2 brackets out of these many 2n brackets we have. Because x1 appears only in the first 2 brackets, x2 only in the next 2, and so on. So the degree in each xi, each yi, each zi is at most 2. So each ai, bi, and ci is either 0, 1, or 2. So you shouldn't have too many monomials actually here, and this monomial is a slice. Okay, and the interesting thing to notice is that because these add up at most 2n, then one of these degrees, either the x or the y or the z degree, is at most a third of the whole thing. So one of these, one of the degrees in the x, y, or z variables is at most 2n over 3, always. They can't all be bigger than that. And the idea is that you arrange these monomials now according to when that happens. So first you bring together all the monomials where the x degree is small, smaller than a third of 2n. Then those where the y degree satisfies that, and then those where the z degree satisfies that. So here I just wrote that. the monomials where the x degree is small. Then from the rest of the monomials, we look at those where the y degree is small. And finally, we look at the rest of the monomials where necessarily the z degree must be small. And we just write out each of these sums as the big variable x to that degree times other things that depend only on y and z. Okay. So here it is. Here is this first sum. I can write it as a sum of monomials that depend on x. The power, the degree of this, the power here will add up to at most 2n/3, because I'm in that first case. And each single degree can't be large. It's either 2, 0, or 1. And similarly, the other two terms have very similar enumeration. The same. Okay, here arrange those where the y degree is small, and here where the z degree is small. And you see that every sum here, this, they're all slices. Because the variables, so here I have the x variable out, here I have the y variable out, here I have the z variable out. So the slice rank is at most 3, so it's the number of these terms I see at worst, right? So it's at most 3 times the number of admissible the exponents here. They're all the same in all 3. So it's at most 3 times each one. And here I've written that, a slice rank of n, which of course, remember, was the size of our cap set by the slice rank lemma, which we didn't prove. That this diagonal tensor has rank at most 3 times r, where r is the number of monomials we're adding up with. Okay, and these are exactly those with exponent and adding up to at most 2n/3, and each exponent is either 0, 1, or 2. And we're actually done, even though it's not so obvious, because this r happens to be smaller than 0.756 to the n. And that's it. So I will explain this in the end. But I think the point is that this problem we have reduced to, just controlling this r, has nothing to do with cap sets. Okay, so it's just a combinatorial problem about n tuples. And you have to study, you have to have a good idea, clever idea about how to control it, but it's possible. So we will see it, but I think it's more instructive for now to go to the slice rank lemma and explain this. This generalization from 2 dimensions, that a diagonal matrix with non-zero eigenvalues has full rank. And then we will see the trick at the end of this. So let me go forward here. Okay. So we want to show that for any diagonal K-tensor, so think K-dimensional matrix, this is the case, it has full rank. So we know, I say full rank because we have already explained that the slice rank is at most the number of layers. We could write mainly matrix as a sum of its layers. Now the goal is to show the opposite. So let's define gamma to be the slice rank. It means that every time we write n as a sum of slices, we need gamma again. We do. And I want to show that I need at least this many slices. Okay. So that's my goal now, to show that gamma is at least this. Right. So let's write n as a sum of slices. I from 1 to gamma. Slice I. So for every slice, that's a 3 tensor, or let's do the k equals 3 case, and the rest follows similarly. Let's say this is a 3 tensor, so one of the variables will be decoupled from the other 2. So I arrange the slices according to what variable I can take out. So out of the gamma slices, let's say for the first alpha of them, I can take out the x variable. Then for the next, from a plus 1 up to beta, I can take out the y variable. And for the remaining gamma minus the rest, I can take out the z variable. Okay. And the idea here is that we will be testing this three-dimensional matrix against vectors, regular vectors, or one tensors. And we will understand the rank of these things. So what do I mean by testing? If the matrix was two-dimensional, by testing I simply mean multiplying. So testing this matrix against this vector, so I'm using direction x here and direction y here, would be taking the inner product for any fixed y of this line with that line. Okay. So it's the x variables with respect to which I'm inner producting. I'm generalizing that to a three-dimensional matrix. So, by the way, yeah, this will be a one tensor. The result of multiplication of a matrix with a vector is a vector. So it's a one tensor, which means that from 2 dimensions, I lose 1, and I go down to 1 tensors. Now I want to do a similar thing where from a 3 tensor, I'll go down to a 2 tensor. That's just a regular matrix that I understand. Right, so what I will do is exactly the same. I will think of inner producting with respect to the x variable. So I have to choose here, and I'm choosing the x variable. So that's the multiplication of next to the dot and putting an x. I'm multiplying m with v, but with respect to the x variable. So this means that for every fixed y and z, in other words, for every line here, I'm inner producting this line with this line here, just the usual way. So I get the sums of products, just like I would normally. Okay, I'll write it out in a moment, but what is the point here? When you test this three-dimensional matrix against the vector, you're gonna get a tensor that depends on y and z. That's a 2 tensor. So the multiplication reduces the dimensionality by 1. In other words, it's a matrix. It's just a normal, regular, not a normal matrix. It's a standard matrix that is things that we understand. And the idea now is to pick an interesting v to test against. Pick an interesting vector to test against, which will say a lot about the rank of m and its relationship, the slice rank of the original m and its relationship with the size of s. So the way you find your interesting v, you do 2 things. The first is you study the slice rank of this product, or just the regular rank. It's the same thing, it's just a 2-dimensional matrix. Overall possible v mainly. Against, so you relate it to the slice rank of the original matrix. Okay. If you know something about the original slice rank, what can we say about the slice rank of these things? And the other thing you do is that you remember eventually that you're looking at the diagonal matrix. So this was diagonal, remember. That was the kind of matrix we were looking at. So we can see very easily that if we apply it to a tensor, we're going to get a 2-dimensional matrix that's diagonal as well. And that's the other way to study the rank. So study the length of this diagonal. Some entries may be 0 in this case. So we need to understand literally the length of the diagonal. So we have 2 ways to understand the slice rank of these tests. And we want to find the v where these 2, so whatever I get from the first and from the second process, they're very close to each other. So I'm going to get one bound here, and I'm going to get one bound here, and I want to find the V where they're very, very close. And this will mean that I can eventually actually connect the slice rank of M with the size of S. That's the model here. So let's do that. Okay. We want to take the product of our three-dimensional matrix with a vector, and I should write what this means. For every fixed y and z, I am, as I said, taking the inner product of this line with this line, so it should be the sum over all x in S of m of x, y, z times v of x. Okay. So that's the definition, and of course, M, as we said, is the sum of all these slices I have up here, I from 1 to gamma. So when I apply it to V, it means I am applying every slice to V. These are three-dimensional slices, and I'm applying every one to V. So I need to understand how slices, what happens to a slice when I apply a vector to it. And we will notice that there will be a difference between the behavior of these slices when I apply V to them, as opposed to these ones. And the reason will be that the variable x that I have decoupled here at the front is the one with respect to which I am taking the inner product. So that behaves differently with respect to the other ones. So let's take these ones first because they're actually easy. So if I take any I from like alpha plus 1 up to beta, sorry, gamma, I'm interested in slices that, okay, the decoupled variable is not x. Okay, so let's just take a general situation like this. I have a slice of this form, f of, let's say, y times g that contains x and the other variable. Okay, that is a general kind of tensor, that form where the decoupled variable is not x. And I want to apply v to it, so to inner product with the v of x with respect to x. Okay. And now the nice thing is that because x was not the variable outside, it was something else that was outside, that something else can go to the front. So this is f of y times the sum over x. So whatever I get here doesn't depend on x anymore. This, you notice, depends on z only because they add over all x. So this is a slice again. You see, y is outside because it could go outside. And here this depends on u and z. And similarly for these slices here, where the variable z is out, it can still go out of the summation in x. So whenever I apply v to these slices, I'm getting back a slice. Okay. So I'll write this as a sum, or the first alpha slices, which are more obscure, applied to v, plus the sum of the rest of the slices applied to v. And all these, as many as they are slices in one-dimensional load. Now the first bits are a bit more unclear what they are. So let me just take the arbitrary slice of this form. It is of the form, so this is about the case from 1 to alpha. These are the slices I'm looking at. The general one is of the form f of x times g of yz. And I'm inner producting that with v, with respect to x. I cannot take this out anymore. It has to be coupled with v. What I can take out is this, which has 2 coordinates though. So I cannot expect a slice. So this is G of YZ times what remains is the inner product of the vectors F and V. I don't like that, it's not a slice. What I wanted was to understand the slice rank of this thing. So I wanted to write it as a sum of slices. But because I don't like them, I'll make them disappear. I will pick V so that this inner product is 0, so that V is perpendicular to the F's I care about, so that all these first bits I don't understand are killed off. So that's the idea. I will pick V orthogonal to these of I, and when I test my matrix, 3-dimensional matrix against those V's, always this will go away, and the rest will be slices. Okay. So this is how you connect the slice rank of this after testing with the slice rank of the original 3 tensor. You find the space where these slice ranks are small. How do you do that? You take V to be the orthogonal complement of these first alpha vectors. So you define it to be the orthogonal complement of the span of F1 up to F alpha. So by the way, all these are 1 tensors. They can be viewed, all these things can be viewed as elements of F to the size of S. These are vectors that are S long. And I'm just testing against things that are orthogonal to all of them. So I have that for every V in this space, in this orthogonal complement, when I apply the matrix to V, 3-dimensional matrix to this V, this will be killed off. And this will be turned into slices, but just 2-dimensional ones. So this will be the sum of I from a alpha plus 1 up to gamma of some different slices that are 2 tensors now. Which means that the slice rank, the smallest number of slices I need to write this as a sum of slices, is at most gamma minus alpha. So for any V in this orthogonal complement, the slice rank after testing is small. It's at most gamma minus alpha. So I found a space of V's where the slice rank is small. And now I'll pick one V in this universe where the slice rank is as big as possible. Remember, I never used anything about my tensor being diagonal. I completely forgot about that. I will remember it now. Since the matrix is diagonal mainly, when you apply it to a vector, you get back a diagonal matrix. And here is how. That's what I'm saying here, that after applying, I always get diagonal matrix. So of the diagonal, so for A different from B as inputs, when I apply, after testing, when I check at AB, I'm getting the sum of M of X, A, B, B of X. Now A and B are different, and M was diagonal, so all these are 0, and I'm getting 0. Of the diagonal, everything is 0, and therefore this is a diagonal matrix in 2 dimensions. So its like rank is simply the rank. I understand it fully. To understand its rank, I need to see how many non-zero elements it has on the diagonal. Here we are. I apply this to anything of the form AA. This is the sum over all X. M X AA times B of X. And now this is 0 if X is different from A, because M was diagonal. So the only thing that survives is X equals A. Okay. Now these are all the diagonal elements for every A in S, that's what I get. But this is always non-zero. This may be 0 though, for some elements along the diagonal. for some A's. So the slice rank, in other words, the regular rank, because it's two-dimensional, is simply the size of the support of V, the V we tested against. For any V, and specifically in the space we were in before, this will be the case. And now I take the previous bound on this one. So for every V in this universe, I had the uniformly controlled slice ranks. But now I know exactly what the slice rank is for any single V. So I have that for any V in this universe, the gamma minus alpha, the upper bound on the slice ranks, is at least the support of that V. And the most interesting lower bound comes from the V with largest support. So use V in the universe with maximal support. This should give you the most interesting bound you can get from this inequality. And it should tell you something about the original slice rank. Now, I have just rewritten that. Well, where does V live? And it lives in a specific vector space inside F to the S, and they just need to pick a V of maximal support, right? It should make a lot of sense that the maximal support of a vector in this universe should be at least the degrees of freedom in that universe. I will not prove this, but I feel it's sort of obvious in some sense that if a universe admits a certain number of degrees of freedom, then the vector with most non-zero points in it should be at least that long. But you can prove it quite easily. Just linear algebra has nothing to do with slice ranks. And then we just need to understand this dimension. This is the dimension of the ambient space, so F to the S, minus the dimension of this span. So it would be equal to this minus alpha if the Fi's were independent, but we don't know they are, so it's at least this. And we're done, because this uniform upper bound on the slice ranks is at least this specific slice rank. So gamma is at least the size of S. And this gamma was the slice rank of M. So for a diagonal K tensor, you have full rank. I think this is nice. I like it. I should do what I promised and go back to this capset problem and show how to control this R. Now this analysis has nothing to do with slice ranks. Okay, it was a number that had to do with finding all n tuples that satisfy certain things. So here are the numbers I have to fill up. They have to give values to them, either zeros or ones or twos. So I have to distribute zeros, ones, and twos in these n positions, so that if I add those numbers up, I get at most 2n/3. Okay, so in how many ways can I do that? That's the R I care about. First of all, I decide how many zeros, how many ones, and how many twos I will distribute. So that is first a choice I need to make. These are M0, M1, and M2 quantities of zeros, ones, and twos. And of course, they should satisfy certain things. So they should satisfy that the number of zeros, the number of ones, and the number of twos covers up these n positions. So M0 plus M1 plus M2 should be n. And also they should satisfy that when you add up the zeros together, so that is M0 times 0, when you add to that ones and you add then the twos, you should be getting at most 2n/3. So any M0, M1, M2 quantities that are admissible in the sense are okay to use. So then I need over all these admissible quantities to see, if I fix them, how many ways there are to distribute the zeros, ones, and twos, given three quantities. So once you decide on your m0 and 1 and 2, you just have to pick m0 positions out of these n to put the zeros. From there, that's how you do that. Then from the remaining positions, you choose m1 to put the ones, and then the rest are just m2, where you put the twos. And you get this many ways. So for any admissible triple, this is the number of ways you have to distribute. Therefore, R is the sum of these quantities, these ways here, over all admissible triples. And the reason I've made red this bound to n over 3 is that if this restriction wasn't there, so I just had this first equality, this would appear in the multinomial theorem. And that is why we write that out. That's R with the restriction. And now I write out a multinomial theorem that says if you have n brackets, you have to pick x to the 0 from n0 brackets, x to the 1 from n1 brackets, and x squared from the other brackets to construct all your powers. And this coefficient was exactly this. We saw it earlier. So here in the multinomial theorem, we don't have a further restriction other than this. In any case, these are very connected. So the first attempt that will fail is to use x equals 1 on both sides. So on the one side, you get 3 to the n. On the other side, the x's all become 1s. So you're getting a bigger sum equal to 3 to the n. That big sum is at least R. R had restrictions, so it was only part of this. So we're not yet where we wanted. This is at most 3 to the n, which is trivial. So the idea is to notice that the exponents that you care about in the multinomial theorem that you want to utilize are those where m1 plus 2 and 2 minus 2n over 3 is negative. These are the exponents we actually care about. So we will divide everywhere by x to the 2n over 3, both sides. So this is minus 2n over 3. So now I care about the negative exponents, the monomials with negative exponents. I want to make those dominant, the monomials with negative exponents. So I'll simply use x that's small, between 0 and 1. So if you use such x, you make big the monomials that you actually care about. So you can easily forget about the others. You can now take this inequality that this big sum is at least the one that corresponds to R, but you haven't lost much if you think of x being between 0 and 1. And for x between 0 and 1, this is a very negative exponent, so this is at least 1 for x between 0 and 1. And therefore, this is at least R, no matter what x I use. So R is always at most this quantity here. I just minimize it. Here is a quantity f of x inside the power n. So minimize f of x. It's minimized for x naught equals to root 33 minus 1 over 8. And therefore, R is at most f of x naught is for this specific x naught to the n. And you get that this is smaller if you calculate this, and then 2.756 to the n. And that's it. And it has nothing to do, it's just a calculation, it's very clever, but it has nothing to do with slice racks. And that's it, yeah. This method is very good to understand sets that avoid patterns. Because of this, so you want to create a tensor that normally would vanish at the pattern and on the, would not vanish at the pattern and on the diagonal. But if the pattern doesn't exist, then it would only not vanish on the diagonal. So avoiding patterns is very good. Works well with this. Yeah, I'll stop here.